Hello everyone, welcome back. In the last class we started discussion about the turbulent flows, and we saw that how the turbulent flow is represented by very disorganized flow where there is a lot of mixing, and we introduced a term called eddy. Okay, basically that is responsible for those kind of mixing. Okay, we will look about the role of the eddies again today, and we started talking about the boundary layer. Okay, in the laminar boundary layer, you can talk about, let us say, the Blasius boundary layer if there is no pressure gradient, or you can talk about the Fachner-Sken gradient boundary layer, and you can represent the laminar boundary layer easily. For the turbulent flow case, we discussed that there are several layers. Okay, first we can broadly classify into the inner layer and the outer layer, and within the inner layer you have several layers, right. So let us look at those layers and how do we get the laws for those layers in the today's class. Okay, so we have this inner layer, right. So let me draw the boundary layer again. Okay. Okay. So you have, okay, let's go really start from here. This is velocity is going to, this is very important that your velocity goes to 0 at the wall, and we will have the inner layer in this region, okay, where the viscosity effects are important, and we will have the outer layer here, and in between we will have the overlap layer. Okay. And this is the outer layer. Okay. Now let us, within the inner layer we discussed that we have this viscous sublayer. Okay, there is here viscous sublayer. Okay, it is also called a laminar sublayer, but I think the more common terminology nowadays is the viscous sublayer. Okay. So remember, this is a turbulent flow. We are talking about the turbulent mean flow. So what I am plotting here is, this is my u hat or u bar, you can call it, and this is your distance from the wall. Okay, you can call it y, right. So if it is becoming 1, okay, this is value 1, that means it has gone to the free stream, right. So let us talk about the viscous sublayer. Okay, and we said that the Prandtl and Corman said that in this sublayer the most important factors are basically your wall shear stress, your density, and your velocity, okay, and the distance from the wall. Let me call it y. Okay, and the free stream pressure does not play a role here. So the free stream pressure acts on the outer layer, okay, not in the inner layer, and this is the layer which is very close to the wall. This is the most close to the wall, viscous sublayer. Now in this region the most of the stresses will be developed due to the viscosity, right. So the turbulence does not play a role here. Okay, so what we can say that we can use the Newton's law of viscosity, and your wall shear stress will be given by mu del u by del y, right. Now we can construct some non-dimensional numbers here. Okay, so we will construct two non-dimensional number here. So first is your tau w is given, right. So I will write tau w as rho u tau square. Okay, what is u tau here? So u tau is called the friction velocity. Okay, why we need to introduce u tau? Because you know the free stream velocity, let us say that free stream velocity here is u infinity, okay, but that wall is not seeing the free stream velocity. It is affected, you would see that it is affected why the wall shear stress, the density and the velocity very close to the wall, okay, and we do not know what that velocity is, and the distance from the wall, right. It is not the free stream velocity. So, we need to find out a parameter for the velocity when you define it, so that we can make our scaling arguments, right. So, you can see this is the stress. So, stress can be written as rho u square. So, we can define a new velocity. Remember, this velocity cannot be measured by an instrument. Okay. So, we are defining it for our convenience, so that we can make the scaling argument, right. So, you can write u tau is equal to square root of tau w by rho, right. So, we can define, if you want to say that how my velocity varies in the viscous sublayer. Okay. So, then let us say this is my velocity which is varying in the viscous sublayer. I will define a quantity u by u tau. I will call that quantity u plus. Okay. So, this is my non-dimensional velocity that I define. Okay. What I am interested in that how the velocity is varying in the viscous sublayer, that is my first question. Okay. Then I look at the other layers also. So, we define the velocity u plus, and secondly we can also define the non-dimensional distance, right. So, I will define a distance called y plus. Okay. I am looking for a non-dimensionalization or the scale for the velocity y. So, on top it will be y, okay, and what should be the at the bottom? I need to use all these things. Okay. You can also use the viscosity here. Okay. So, if you make the scaling argument, so this is in meter, right, and then you have nu by u, right. So, nu is kinematic viscosity meter square per second, and u is meter per second. So, if you do nu by u, that will become meter, right. So, or it can be written as y, I will write u tau, right, because that is my velocity that is defined here, y u tau by nu. Okay. So, I have defined a y plus here. Now, many of you who have already used CFD to some extent, let us say use a software or something, you would be hearing this term again and again, it's called y plus, right. If you let us say do a turbulent flow simulation, the first question that will be asked to you is that what is the wall y plus you have. That means it is a measure of distance, and if you let us say use very high y plus, then you are basically ignoring the viscous sublayer, you are not resolving that sublayer, right. So, we will come to that again. So, if you write all this in terms of this, so your tau w is equal to mu del u by del y, right. So, you can write it rho u tau square, okay, is equal to mu del u by del y, and then you can make this argument that you can just, because it varies linearly, right. So, you can just write y by u by y, okay, mu u by y, right, because it is we are talking about the layer very close to the body. So, then you can reorganize it, okay, and you can take this y on the right left hand side. So, this is rho u tau y by mu is equal to u by u tau, right. I have just reorganized these two terms. Okay. What is this thing? This is y u tau by nu, okay, and this is your u by u tau. So, that means we got y plus equal to u plus, or basically u plus is equal to y plus. So, in terms of non-dimensional velocity and non-dimensional distance, they are basically there is a linear relationship in this viscous sublayer. Okay. So, that is what we figured out from this argument, that the only stress that dominates close to the wall, very close to the wall in the viscous sublayer is the only the viscous stress, okay. And that is why we could take this relation tau w mu del u by del y, and for a very small distance del u by del y can be written as u by y, and finally you get y plus equal to u plus. Remember, this is for a very small distance close to the wall. Okay. Now, we go to the layer which is slightly away from the viscous sublayer. Okay. So, in that distance we will call that region, I mean there is no name for the region, I mean, or you can call this say log law region. Okay. Why it is called log law region, it will become clear very soon. Okay. And we will say that in this region the dominant stress is the turbulent stress. Okay, what is turbulent stress? So, remember when we are talking about a turbulent flow, it has got fluctuations, and these fluctuations basically interact to each other, and they generate momentum additional to the mean flow momentum that you have, right. So, you have a flow, as we saw the picture earlier in the last class, that we had the mean flow like this, and we had this fluctuation which was like this, right. This is the instantaneous measurement, the blue one, and the black one is the mean flow measurement. So, you can basically break into two parts, and that is the crux of the RAN simulation that we do, that we take this mean flow and then we take this fluctuations separately, okay, and we add the both together to get the total flow, right. So, we say that this turbulent stresses, the stresses generated by the fluctuations play a key role in the log law region, which is away from your viscous sublayer. Okay. So, in that case we can make the scaling argument that your del u by del y, okay. Remember so I should actually really use u bar, okay, because we are talking about the mean flow. Okay. So, everywhere you have, so this is u plus is basically u bar by u tau, okay, because if you talk about the just u, so u is basically u bar plus u fluctuations, this is my fluctuations, that gives you the stresses, right. So, I am saying that the velocity gradient here, it is basically proportional to the u tau by y, okay, by making the dimensional argument. So, this is from the dimensional argument. And considering that my viscous stress is not that important here, but the so viscosity is not very important here, but indirectly the viscous effect is coming through the wall shear stress. Okay. So, then what we can do, we can use a proportionality constant d by dy is equal to 1 by kappa u tau by y. Okay. This kappa is called the von Karman constant. Karman was a student of Prandtl, okay, who made key contributions in understanding the boundary layer. In fact, before Prandtl, there was not much understanding about the boundary layer, and Prandtl being an engineer, people believed before Prandtl that if the flow becomes highly turbulent, anyway the layer, the boundary layer is very thin, right. As you keep on increasing the Reynolds number, the region where the effect of the viscosity exists is very close to the wall, it becomes thinner and thinner. So, people thought that you can ignore the effects of the viscosity, right, if the flow becomes very turbulent, right. And because of that, they actually ran into a problem that is called the D-Lambert's paradox. Is basically they found that there is zero drag, okay, in certain situations. For example, if you can do on a flow based cylinder, right, because they ignored the effect of viscosity, it becomes, the layer becomes very thin, but at the same time the flow gradient increases, the del u by del y increases to a very high level, and that plays a very important role in calculating the drag. So, since they ignored before Prandtl, so they could not figure out how the drag is happening. It was Prandtl who introduced the boundary layer, and he said that you cannot ignore the boundary layer no matter how turbulent your flow is, no matter how high Reynolds number is. In fact, if your Reynolds number is very high, the layer is very thin, and then at the same time the wall gradient is very high. Okay. So, that means the drag will be higher, right. So, this is after Karman. So, this is called von Karman constant. Now, you can basically integrate it, okay, and you can use the proportionality constant, and it will become u bar by u tau. Okay, I am just keeping some steps here. Okay, so 1 by kappa log y u tau by nu and plus b. Okay. This b is coming because of the proportionality constant, sorry, because you have one integrated. So, you will have a additional term which is coming. Okay. So, that is the term which is b, and this b is called intercept. Okay, and this is your one common constant, okay, that we already written. So, typically this value of Kalman constant is taken as 0.41, okay, and the intercept value, it is not a constant value, but typically it is around 5 to 5.5 or so. Okay. Remember, this Kalman constant 0.41 is considered to be a universal constant, while the intercept is not a universal constant, it depends on the flow. However, recent studies show that let us say if your flow is relaminarizing, that means it is becoming from turbulent to laminar, or even in some other situations this one Kalman constant may fluctuate slightly. Okay. But that is a different topic of discussion. As of now, we found a law of the wall, okay, which is the log law. So, that if this is u plus is equal to 1 by kappa log y plus b, okay, and if you use the value of 0.4 and 5, you can write as u plus is equal to 1 by, so this is around 2.5, right, 1 by 4.4. So, it will be around 2.5 log y plus, okay, and plus 5 or 5.5. Okay, let me put everything in the plot, or let me just show you the plot. Okay. Yeah, so this we have already discussed. Okay, this is 0.41 and 0.5. Okay. And this is the plot that I wanted to show you, right. So, this is the viscous sublayer which is very close to the body. Remember, this is u plus equal to y plus. So, if you plot it here, okay, now your axis is in log scale. This is something which is very important to remember. There are many students who get confused while looking at the plot, because they do not realize that it is in the log scale. So, now it is in log scale, okay, log y plus, log e y plus, or ln y plus, and this is your u plus, right. Now, what is there in the viscous sublayer? U plus is equal to ln y plus, right. This is a viscous sublayer. So, how will it look like in this curve? It will look like this, okay, it will go like this. Okay. So, this is your look little bit like line, let me erase it. Okay. So, it will be like this, okay, and you can so this is my log layer u plus equal to ln y plus, okay, and this happens up till y plus equal to 5. Okay. So, let us say you are not using y plus less than 1 in your simulation, that means you are not resolving the viscous sublayer. Okay. Of course, there are some wall functions which can tell you, which can feed this function for you, and it allows you to use a higher value of y plus. But if you are solving to the wall, you must ensure that you are solving the viscous sublayer also. Then you must have at least 5 grid points to solve that layer. So, if y plus equal to 5, then you need y plus less than 1 to basically resolve the viscous sublayer properly, right. And then in between you have this buffer region where none of these laws are valid, okay. And then after from like y plus equal to 30, okay, now we have the law of the wall, okay. So, you can have this straight line, okay, which is your law of the wall, that is basically u plus is equal to 1 by kappa ln y plus b. Why it becomes straight line? Because this one is ln y plus, right, or log e y plus. So, that is why it is a straight line, and in between none of the laws are valid and they can be smoothly connected, Okay, so it can be connected like this. Okay, so in fact, Spalding proposed a law later which basically connects smoothly. I mean, say single law which takes your u plus equal to y plus. Okay, no, this is not ln y plus. Okay, in the log law, this is u plus equal to y plus, not ln y plus. Pardon my mistake. Okay, so this region is u plus equal to y plus. Okay, that's why it is not a straight line. Okay, so u plus equal to y plus and u plus equal to 1 by kappa ln y plus b. So Spalding proposed a law which basically connects this region smoothly, and after that, if you go to so it starts at the law of the wall starts at y plus equal to 30, and it depends on what kind of bond layer you have. It can go to a very high value. It can go to 500, it can go to 100 or 300. Okay, and after that you will have the outer layer which will start. Okay, this after that you will have the beginning of the outer layer. Okay, where the law of the wake will be applicable. Okay, whatever model we are using must basically predict these values accurately for the mean flow. Okay. Spalding. Okay, you can look at the same thing here. So this is your u plus equal to y plus, and this is your log law. Okay, and this is the region. It started at around y plus equal to 30, and in this particular case, it may be a flow in a channel or a flat plate. It is going up to like a couple of hundred, but let us say if you have a atmospheric bond layer, it can go to very high value. Okay, in the outer region, it will not be detected by the log law, but you will need to consider the free stream pressure gradient, the bond layer thickness. So there the scale will be u by u infinity and not the u by u tau. So here we have used u by u tau as the scale, but if you go to away from the outer layer, your scale is u by u infinity. Okay, and this is the pictorial representation of the stresses, how it dominates. So this one that you see is the turbulent stress. Okay, it is written as rho u prime v prime bar. Okay, so it is written as rho u prime v prime bar. Okay, so there is a meaning to that. One thing you can immediately see that this relates to the fluctuations, and when the fluctuations basically talk to each other, they generate some kind of stress, right. So this is the turbulent stress and this is the viscous stress. This is the viscous stress. Okay. So you can see that very close to the wall in the viscous sublayer, the most dominant stress is the viscous stress. Okay. Outside you can see that the most dominant is the turbulent stress, but you can see that the summation of both in the inner layer is constant, right. So here the viscous stress is going down. Initially it was the only stress and the turbulent stress was 0, but then viscous stress is going down and the turbulent stress started increasing. By the time we went to the log law region, the turbulent stress become more dominant, right. So the summation of this remains constant. This is also called the constant stress layer, the inner layer, right, because the summation of the viscous stress and turbulent stress is constant there. Okay, and after that you have the overlap layer and the outer layer. Okay, so this will come back to this picture again when we talk about the different turbulence models. Okay, we will soon go to the turbulence models. First we have to derive the governing equations. Okay. Now let us come back to the question that we initially asked, that why simulating turbulent flow is difficult, right. Now turbulent flow can be considered as basically there are several eddies in the flow. We looked at the jet flow, we had several eddies, right, from very small eddy to very high eddy, very big size eddy. If you let us say if you talk about flow in a channel, okay, this is a channel flow. Okay, then you can have the largest eddy, okay, which can be like as big as this, or you can have very small eddy, very small eddy, which is like this, right. So if you want to basically simulate this flow, you need to resolve the largest eddy. This is your largest eddy and this is smallest eddy. Okay, so you need to resolve both the largest eddy as well as the smallest eddy. So your grid should be basically smaller than the smallest eddy size. And the big picture is that this largest eddy, they get the energy from the mean flow. Okay, there is a mean flow. So we have this u bar and plus u prime. So this is a mean flow, which is the main flow that we see when we average the flow, and this mean flow gives the energy to your largest eddy, and this largest eddy transfer the energy to the next size eddy. Okay, and then it will further transfer to the next size eddy. I have only shown the 3 eddies, but you will have a complete energy cascade. Okay, it starts from the very large eddy and go to the very small eddy. Okay, if you look at the cascade picture, this is your energy cascade E k versus k. So k you can think of as the inverse of the eddy size. Okay, so wave number is inverse of the eddy size. So if it is bigger, then the eddy is smaller, right? So this is the smallest eddy, and this is your, let us say, your largest eddy, right. So this largest eddy getting energy from the mean flow, it transferred to the next k, next k, next k, basically next eddy, next eddy, next eddy, till the time it goes there where it becomes so small that now viscosity can act on it and then it dissipates in terms of heat, right. So it got the energy from the mean flow, transferred to the next eddy transferred to the next eddy, next eddy transferred to the next eddy, and then so on and so forth, and goes to the very small eddy size where the dissipation happens. Let us say your grid is not resolving the smallest eddy here, right. So you are not basically dissipating the heat fast enough, right. Your dissipation rate is not basically according to what should happen to the physics. It is not true to the physics, right. So your energy will keep on accumulating, your solution will ultimately blow up, right. You are not respecting the energy cascade if you are doing a direct simulation. So there is a very nice little poem by Richardson, which talks about that big holes you can think of the eddies, the big holes have little holes which feed on their velocity, okay, because we get the energy from the mean flow, and the little holes of lesser holes so on to the viscosity. Okay, so it goes on till the viscosity starts acting and it gets dissipated, and this is the energy cascade again represented in a different way. You have the largest eddy, you have the smallest eddy, there is energy cascade in between, and then there is a dissipation happening, the production happening because of the mean flow here. Okay, and this picture again is very important, how the energy cascade works, and when we talk about the K epsilon turbulence model, we will look into this picture again. Okay, now there are many approaches to solve this problem. Okay, coming back to the big question that we initially asked when we started this discussion turbulent flow, that why it is difficult to simulate a turbulent flow, right. So if you want to simulate a turbulent flow, let us say using an approach called DNS, there are 3 approaches mainly, DNS, LES and RANS. Of course, there are intermediate approaches, or there are approaches which are like a partial DNS, partial LES, partial RANS. Okay, they are called the detached eddy simulation, okay, DES. Okay, but mainly 3 classical approaches. Only the direct numerical simulation, where we use the basically Navier-Stokes equation that we have, but you have to make sure that you are resolving all the gradients from the smallest size to the largest size. Okay, so your grid should be very fine, so much fine that it can basically resolve the smallest eddy size, which is given by mathematician called Kolmogorov, and he talked about the smallest eddy size, and it typically goes as Reynolds number to the power minus 3/4. Okay, or the grid size, if we talk about, is if it is this in 1 dimension, in 3 dimension this will become r e to the power 9/4. Okay, this is your typical grid size. Okay, in 3 dimension, this is the size of the smallest grid. Okay, this is the smallest grids. Okay, and instead of grid size, let me use the word grid count. Okay, so your grid count goes at Reynolds number to the power 9/4. And if you talk about like the time is also like your delta t is also going as delta x, following the current condition that we are talking about, then your computational power goes as r e to the power 9 by 4 into r e to the power 3 by 4, which is basically r e cube. Okay. So, if your Reynolds number is 10 to the power 6, which is a typical Reynolds number for flow over a wing, you are talking about a computational power which has to solve a grid size of 10 to the power 18, okay, 10 to the power 6 power cube, right. So, this is, you can see that even on a exaflop machine, it will take a very long time. Okay. So, that is why this approach is very expensive, resolving to the finest grid, and we typically avoid this approach, or we basically cannot use this approach for a complex problem at realistic Reynolds number. The other approach is large eddy simulation. Okay. Those who could not follow this will come back to this picture of the Kolmogorov scaling when we talk about the LES, okay, the large eddy simulation. In the large eddy simulation, we basically resolve the large eddies, okay, which are responsible for the most of the dynamical behavior in the flow. As we discussed, the smallest eddy typically play a role in dissipating. So, right. So, we can basically cut down the our simulation somewhere and start modeling the very small eddies, right. So, there is a difference between modeling and simulation. Simulation is, we are basically respecting the equations and solving it as it is using our numerical model, right, numerical approach, your discretization scheme, flux scheme, so on and so forth, right. In the model, we use some kind of turbulence model, and we, instead of solving the eddies or simulating the eddies, we basically model the effect of the eddies somehow into our simulation. So, this is what happens in the LES. And finally, what is our main topic of discussion is the Reynolds average Navier-Stokes. Okay, this does not use the Navier-Stokes equation directly. This uses another form of Navier-Stokes. Okay, not form, but another averaged version of the Navier-Stokes, which is called the Reynolds average Navier-Stokes equation. And here we do not simulate any eddy, but we get the effect of eddies using a turbulence model. And the turbulence model may depend on the flow that we have, and what kind of geometry that we have, what kind of situation that we have. Let us say it has got a separation or transition or some other thing, then you will have a different turbulence model. Let us say it is fully developed, okay, then you will have different kind of turbulence model, and so on and so forth, right. So, the DNS is the most expensive, okay, LES is intermediate, and the range is the least expensive. Okay. So, this is basically is the first tool that an industry uses when they want to design, but as you know that we are not completely simulating the eddies. So, we are missing some of the physics. Okay. We are not completely using the physics, and sometimes your model does not give you the correct answer also. The model are basically developed using some empirical relations, some experimental observations, and they may not be completely accurate. Okay. So, that is a very big problem, but unfortunately, this is the only thing that gives you the solution in a reasonable time. The LES is also now becoming popular because of the arrival of the GPUs, and you can simulate the flows in a reasonable time. So, this is also now becoming popular, but DNS is still, we are very far from using it for the practical flow situations. Just use some flow, so some pictures. So, this is from range to DNS. You can see that here we are resolving only the mean flow. Okay, this is a turbulent flow, and DNS we are resolving all small scales. Okay, and the LES we are resolving some scales, but we are missing the very small scales. In between, you can have unsteady range where it is range, but if you have certain changes in time, the broad changes in time, that can be basically captured here, and hybrid is basically in between range and LES. Okay, we will skip here, and you can see that here you have got range. This is the mean flow. This is how the DNS looks. This is a flow, I mean picture of a flame. Okay, realistic simulation. Okay, and this is the LES where you capture the mean flow plus some fluctuations, but not the very small fluctuations as we are seeing in the DNS here. Okay. So, what we will do in the next class, we will start getting the full picture of the RANs. Okay, we will start the RANs equations first for incompressible, then for compressible, and then we see what are the turbulence model that we require to solve this problem, solve these kind of problems. Okay. With that, thank you very much. We will meet in the next class.